Now, another word that you will hear a lot in statistical mechanics is called a partition function. So without going into too much detail about what a partition function is, let me define that very simply in a very few words. So what is a partition function? Partition function basically describes the statistical properties of the system in thermal equilibrium. Partition functions are described as they are needed, and they may have many physical interpretations and meanings depending on the situation under consideration. It expresses the number of thermally accessible states that a system provides to carriers, for example, electrons. Partition functions are functions of state variables such as temperature and volume and chemical potential and more. They are generally dimensionless. They are just pure numbers. And each partition function is constructed specifically to represent a particular statistical ensemble. Basically, partition functions tell us the number of microstates accessible to our system in a given ensemble. For example, a canonical partition function applies to the canonical ensemble when the system exchanges heat energy at T, V, and N fixed. Whereas a grand canonical partition function applies to a grand canonical ensemble, where the grand canonical partition function applies to the grand canonical ensemble when the system can exchange heat with both heat and particles with mu, T, and V fixed with the environment. So what is a partition function? Partition function describes the statistical properties of the system in thermal equilibrium. They are defined as needed. They are dimensionless. And they may have many physical meanings depending on the situation. What they basically do is that they tell you the number of thermally accessible states that a system provides. They are functions of state variables. And state variables includes T, V, mu, and et cetera, et cetera, et cetera. And each partition function is constructed to represent a particular statistical ensemble. And usually the symbol for a partition function is a fancy looking Z. So if we assume we have a system of n particles, and there are certain possible quantum states available to the particles, and the energy cost of putting the particle into the ith state is EI, then the partition function of our system is given mathematically as Z equals E mu Ni minus EI divided by KT, sum over I. Where I is the state of the system, and if we put Ni particles into the ith state, then Ni will just be called the occupation number. The same occupation number that we have been talking about of the ith state. And the particular configuration of our system will be given by the product sum over N alpha, the product over alpha, e to the N alpha divided by KT mu minus E alpha, where note NA N alpha is a set of occupation numbers allowed by the symmetry of the particles, which means two different kinds could exist. Which were they? Fermions and bosons. So for fermions, N alpha will just be a state either 0 or 1. And for bosons, N alpha will just be a state. Well, N alpha could have any number of particles, 1, 2, 3, and so on.